Up next, Tom Clark, K3IO, with an AMSAT update.
Rather than the title that Steve gave you, I took the author's opportunity to redefine this. I'm going to describe an activity that I've personally been involved in for the last, roughly year. And I'll tell you how we got there. But this involves my ideas on geostationary satellite for amateur radio. And as you'll see a little later on, we're looking for opportunities right now. I do want to make a big disclaimer here that even though I am a member of AMSAT's board of directors and you know me associated with AMSAT, these are my comments. They're not in any way AMSAT official. And I even go ahead and sign the document for you. So I want to start out here by looking at what AMSAT said our mission and vision were. And this was done in 2004. We're a nonprofit organization. We build satellites and try to handle some education in terms of just what is space. But our vision is to deploy a high Earth orbit satellite systems that'll give at least once per day coverage by 2009 and continuous coverage by 2012. Now this was what we said in 2004. I am usually asked if I'm serious with that statement, 24/7 operation by 2011 or 12. Are you serious? Well, yes, we were serious, but we lost a little practicality. When that vision statement was written some 4 years ago, the initial step was to be accomplished by AMSAT Germany's Phase 3E satellite flying by basically now. AMSAT NA is fully supporting AMSAT DL in any way we can. That's financial and with technical assistance. But we're committed to, or we were committed to doing a payload we called Eagle for a new next generation of high Earth orbiting satellites. HEO is high Earth orbiting. You'll also see LEO for low Earth orbiting. Both Phase 3E and Eagle depended on the availability of suitable launches. Specifically, the desirable part of the launch is the ones used for as the first step of geostationary transfer orbits. It's an elliptical orbit, which we have to then carry a motor and fire it to get the final orbit that we want. But in the real world, there ain't no such thing as a free launch. Tonstoffel, for those of you who are science fiction devotees. AMSAT DL has had an amazing record of getting launches on the Ariane vehicles, arranged because the AMSAT DL people are held in very high esteem by the European professional aerospace community. AO10, 13, and AO40 made it to orbit. Phase 3A was the one that in 1980 decided it wanted to have a subterrestrial perigee. And in fact, it was a wet perigee. Some of you may remember that. Now, Carl Meinzer, the brains behind AMSAT DL, has had a lifetime dream of a program he's called Phase 5. In our AMSAT nomenclature, Phase 3 were these high-altitude elliptical orbit satellites. Phase 4 was for geostationary satellites. Phase 5 was for other. And Phase 5, P5A, is an independent, built by amateurs mission to Mars to take place sometime in this next decade. Under German rules, however, Carl was forced to retire a couple of years ago. He also has become a curmudgeonly old fart now. With that went some of his resources that he was bringing to the amateur satellite program, specifically a major laboratory facility at the University of Marburg. That's about 60 or 70 kilometers from Frankfurt. At the Central Electronics Laboratory. Those have dried up now. In fact, the ZEL is out of business. Over on this side of the pond, we've been trying to find suitable GTO launches. Lee McLam, KU4OS, who's a professional in the aerospace community down near the Cape, has attended many small sat meetings, rideshare meetings, and so forth. Suitable GTO launches are very few and far between. They come with a cost forecast for a piggyback ride in the $2 to $10 million range. Needless to say, that number exceeds the threshold of pain for an amateur project, but the number is real. And even in low Earth orbit, the satellites are starting to cost more. The Russians have been selling launches of SS-18 and 19 ICBMs, especially from Kazakhstan, in conjunction also with the Ukrainians, and priced at something around $20,000 per kilogram. That price has been creeping up, and those launches have been getting tougher and tougher to obtain, because the Russians don't have that many SS-18s and 19s in flyable condition, and those are, the people who maintain them and make them so they'll work, are all getting old and feeble and retiring. So the brain power necessary to launch these old things is also declining, so the Russian prices are now significantly higher than those that applied earlier. Well, let me now talk about the Eagle project and what it was. It involved, as a fairly simple high-altitude satellite in an elliptical orbit, followed a lot of the design ideas that Carl Mainzer had for smaller satellites, which is all of the AMSAT DL things except AO40, which was definitely not a small satellite. The initial strawman design for the Eagle payload looked something like this. It had some fold-out wings to give us a little more surface area. It was supposed to spin about an axis that goes through like that. In other words, it's supposed to be, it is spinning, and spin stabilization is important to these satellites. Unfortunately, the satellite wasn't very well balanced, and there was a lot of concern that it was just going to wobble too much. And that's a pain because you have to orient it properly in order to burn the motor, which you got to have in order to be able to live more than a few weeks. And you want to then change to a different orientation so the antennas point at the Earth. So that evolved into a more symmetric structure, a six-sided one. This is just a top view. This one was one where I showed one of the geometries for active dynamically phased arrays that I had been proposing as the way to handle the antennas here. But it was a six-sided thing, looking about like that. The RF hardware is that goes into one of these is what we all think of as amateur radio. It included things like phased array antennas and stuff like that, so it was advanced amateur radio. But then in addition, these satellites had to carry an apogee kick motor with associated fuel tanks, plumbing, valves, and so forth. And AMSAT has not had the best track record in history with kick motors. They have been an enigma for various reasons on every satellite that we've had it. To make the kick motor work, you have to have attitude determination hardware on board to figure out which way the satellite is pointing to fire the kick motor and to point the antennas after you get to the right orbit. You have to have some way to spin it and torque it around, and that was done with magnetic torquing, except for the fact that in this elliptical orbit, you had to do all of the torquing when the satellite is closest to the Earth, where the Earth's magnetic field is big enough to be able to torque against it. Out at apogee, when it's at its high point, the magnetic field is too weak to be able to do any active positioning. So every 12 or so hours as the satellite comes zipping by, that's when you have to apply all of the commands that spin it up. It takes a lot of solar panels. The satellites we were talking about required something around 100 watts each. For the geometry you saw a little bit earlier, that if we paid retail price for it was about $2 million worth of solar panels. And to make all of those things play, you need some sort of a real-time multitasking control computer that works, and it has to be very reliable. Needless to say, items 2 through 6 are not really parts of amateur radio. They're amateur space, but they aren't amateur radio. And so there's a limited number of people in the world who have been able to handle some of those things. Well, we started looking for other alternatives, and geocentric satellites, geostationary satellites, turnout are certainly competitive in price, and we can simply go along with somebody else who's going. Well, that turned on the light bulb very brightly. We still have to supply all the same RF and digital hardware that we did for the elliptical orbiter, but there's no kick motor. And they supply all of the attitude control pointing back with the whole body of the spacecraft pointing back at the Earth to levels of something like 1 or 2 degrees. They supply hundreds of watts of power. We would be these things typically have over 10 kilowatts of power available on the satellite. Yes, that's a lot of expensive solar panels. And for us to want a few hundred watts to be able to run our stuff doesn't seem to be a problem to them. And we can have a satellite that now provides us with that 24/7 coverage. And the study, the one we're looking at covers North and South America and much of the Pacific. Oh yes, don't forget, no kick motor is needed. Some of the considerations that went into the design, we've done a lot of work on Eagle, and we want to use as many of the concepts there as are applicable, but doing things at geostationary orbit are different. So in some ways, we have a clean slate to develop many of the ideas, not dependent on the things that we had decided to do for Eagle. For instance, we finally have a way to really justify and defend our valuable microwave allocations. Geostationary satellites lend themselves very nicely to microwave activity, and many of those hundreds of megahertz of spectrum space that we have at frequencies above a gigahertz, they're very much wanted by various commercial sources, and we need to actively justify it. A lot of amateurs now are finding that their houses have CCNR antenna limitations, if we use microwaves, those users that have these problems can use fairly stealthy fixed small dishes of the kind that would have been used for DirecTV or something like that. Our host is designed for at least a 10 to 20 year lifetime, and they make their money by getting more years out of each one of the satellites. We have to therefore design to our best guess as to what will amateur radio be in 2020. Not what is it today, not the legacy stations that we have now. There won't be any FT-847s that are very useful. But what are we going to have in 2020? So I'm going to give you a couple of design premises here. All future satellites will be concentrating on microwave frequency. Certainly any high altitude satellites will. And here is the microwave band allocation from 1 gigahertz up to 25 gigahertz. And here we see one important distinction. The amateur radio service, what you can use terrestrially, has that set of bandwidths, including on the 3300 megahertz band, 200 full megahertz of bandwidth available. Whenever you have your satellite operating point to point to your neighbor, you are in the amateur service. Whenever you point the satellite, the antenna up at space and talk to the same guy, but using a satellite, you are now in a totally different service as recognized by the ITU. It's the amateur satellite service. I sometimes worry that they picked the initials ASS for that. Second premise, you're going to need antennas that are about 1 meter in diameter. Why 1 meter? Well, 1 meter is as good as another. Here is a table that shows what will a 1 meter dish do at all of these frequencies, and I've also thrown in as the bottom line in a different color, KU band TV, because that's where these things come from. 1 meter is a little larger than you'll find most of the backyard TV satellite dishes, unless you live in places like Alaska. And there you will use the 1 meter ones. More like 60 centimeters is more typical. Again, I draw attention, because they will be important in things I talk about in a minute, to the 3.4 and 5.7 gigahertz bands. That pair of frequencies, for various reasons, ends up being the place I've found to be the best. And that backyard 1 meter dish gives you gains in the 25 to 30 dB range. Good antenna gain. That means that your milliwatt transmitter looks like a watt, or your 1 watt transmitter looks like a full kilowatt. That makes a big difference. What you might end up seeing here is a couple of direct TV antennas side by side. They might have been transmit and receive on 2 different antennas. That way you don't have to have complicated transfer things. The antennas are small. This particular photograph is of a 2-element interferometer for radio astronomy that was done by one of my colleagues at the Haystack Observatory, and kind of a nifty little project, but it was the best picture I had of a pair of antennas. Okay, back in the good old days, the old spacecraft that we had used simple bent pipe linear translators. That being that the signal comes into a receive, it's converted to some convenient IF, where there's some amount of IF signal processing goes on, bandpass filters and things like that, maybe AGC, passed off then to a transmitting up converter. That's the whole satellite. One of the big issues in that design is the conversion efficiency from DC to RF, especially over on the transmit side, because watts are expensive in space. A secondary issue has been dynamic range. The satellite transponders, like the Mode B transponder on Oscar 7, have been plagued with a lot of user-to-user intermod. The noise floor has been as poor as about 26 dB below the peak power. So that means you didn't have very much dynamic range. You didn't have enough dynamic range to be able to make a very effective AGC. And this is what one of them looked like. This is the transponder, the Mode B transponder on Oscar 7, which came back to life miraculously as a phoenix from the ashes a few years back. And it's still on now, even almost 30 years since the time it was launched. Amazing. The new type of implementation of a linear transponder that some of us have been pushing, especially Bob McGuire and I, is what we've called the SDX, a software-defined transponder. And that's really a software-defined radio running full duplex with some sort of a computer widget in the middle to do the signal processing. This is especially Bob and I, have become convinced that we can do a much better job on signal conditioning using DSP techniques. It really is a big difference. We've talked a lot about doing digital satellites. And the digital satellites that we've talked about have had a signal that has the uplink coming in. It gets converted into bits in some sort of a box. It's demodulated with the FEC that was applied on the ground in order to make the data be high quality, handed over to a remod box, a remodulator, that makes a fresh FEC. It may also change modes. You might end up with an FDMA over here, and this might be CDMA as being the logical communication techniques. Why does that work better? If we did this function just through a bent pipe linear transponder, we would suffer a 1/r² signal loss getting up to this point, and loss in signal-to-noise ratio. And we would have a similar 1/r² path loss, degradation of signal-to-noise ratio on the downlink. Now, we should be running the minimum power possible on the uplink, so we transmit the weakest signal we can that gets into the satellite. That makes it available to more people. And the watts come very near and dear to, in space, so we never have the condition of high signal-to-noise ratio on either link after they've gone through the 1/r². So that means that the total signal-to-noise ratio degradation goes as r to the 4th. Not a happy situation. If we demod, we've got a 1/r² path to here. The bits are now perfect. They get modulated here, and we get a pair of 1/r² links, which in almost all cases wins. If we are able to negotiate a geostationary ride, now I'll talk a little about my initial, here's what I'm thinking about strawman design. You're the first people who have seen this, and so I expect to have boos and cat calls and so forth, but that's okay. We'll make maximum use of the microwave bands. Now in this case, whenever I use that word, I'm talking about the commercial host that is going to give us space or sell us space. And for various reasons, I don't want to discuss who that source is, so the generic word they will appear several times. I just want to make sure you understand who they are or who they aren't. It is a U.S. firm. For various reasons, they use C-band for one of their sets of uplinks. They've also got KU-band, but C-band uplinks in the 6+ gigahertz range. So if we want to put our uplinks at the nearest convenient frequency, so we have minimum RFI problems with them and so forth, that says that we use for uplink the 20 megahertz chunk that I showed earlier from 5650 to 5670 megahertz, 5-centimeter band. That has a good piece of good news. You notice I said transmit. Right now, one of the big problems we've had in our S-band satellites and even for the terrestrial amateurs is that there's an awful lot of Part 5 devices, unlicensed devices, 802.11n, or sorry, N and A both, in fact, wireless telephones, a whole bunch of other stuff using this band and also the 13-centimeter band. And here is our opportunity to transmit so that those folks know we exist. That could be very important to us in protecting and defending our rights to that band. If all of a sudden in a lot of places around the U.S. those bands cease to be very useful, it could be a help. The best match of frequencies for the downlink, the old C-band, big ugly dish band, is just about 4 gigahertz. And the best match for that, which still is fairly open in spectrum, is our 3400 megahertz, 10 megahertz wide allocation, 9 centimeter band. That area is being populated heavily in a lot of developing countries by WiMAX. We may have to do some fighting, and yes, it's a downlink, so we don't get quite the same protection as we might have had. We might also, and you'll see it showing in the diagrams and the pictures to follow, use the band S1. By the way, AMSAT has used the notation of recent time, S1 for the lower frequency S-band allocation, 13 centimeters, right among all 802.11b folks, and S2 being the upper one. So when you see S1 and S2, that's the difference. They're both in what has been classically called S-band, but it's high and low. We might be able to carry along either an uplink or a downlink at that frequency, perhaps both, using only one at a time, though. Antenna space, as you'll see in a couple of minutes, does not permit anything in the way of high gain antennas for 2 meters, 70 centimeters, 23 centimeter bands. They, remember my definition of they, are concerned about possible RFI, especially in their IF range, if we have transmitters that are there in the range of their IFs. So they basically said, we don't want you transmitting. They didn't say we couldn't receive, but since they'll be very low gain antennas, this is definitely QRO, high power world. This makes it so that if we do put any uplinks on that, in that range, the guys with EME arrays will have something to talk to, but I don't think many of the backyard users, the present satellite users, are going to be able to get much signal through. Well, so we were told that the platform we might be riding on might look something like this, and they provided this drawing to us and said, they then said, we'll find some space on the top face, look at this axis here, looks toward Earth, on the top face of that, and we'll see if you can fit something in there. Now, by the way, they've got their high gain dishes, especially for KU band there. They have a lower gain C-band dish that is here that's made out of some sort of a grid-like structure, because if you remember, the geostationary satellites have gone to only using linear polarization, and adjacent channels are done with orthogonal polarization to give better channel-to-channel separation. They said it might fly in 2011. There might be one later. And it might be parked around 130 degrees west. They asked if we could fit into some spaces. I'll show you what they look like in a minute. And for us to provide them with size, weight, and power estimates, which I've done. Now, 130 degrees, isn't that too far west to be useful? Well, that is out over the Pacific. However, in this picture, which comes from one of the GOES weather satellites at around 130 degrees west, you can see that over here, all of the US is covered, most of Canada, most of South America, Hawaii, maybe even New Zealand. And so it's not that bad. You can see that better on this map, which I pulled off of one of the commercial sources websites for, in this case, it was a satellite at 129 west. And these contours over here that arc across are 0, 5, and 10 degree elevation contours. So from the East Coast throughout the US, it's above 10 degrees elevation everywhere except for the very most tip of Alaska, where it's down around 8. I don't think we have too many Eskimo users, so I'm not too worried about that. Hawaii is near the center of the footprint. The contours that they show on this map are what they do with their fancy higher gain arrays. And I have down at the bottom computed elevation angles at different places. Boston's 14.7, Quebec is 13. It's only a half a degree in Newfoundland. Chicago, where we are now, would be 26-degree elevation. Anchorage is 18, and Auckland, New Zealand, down in here is 18. Now, some more stuff on my straw man design. Again, the same caveat emptor comments I make, that these have not been approved by anybody. They are the ranting and ravings of this feeble mind. And they've not been reviewed by any, and volunteers in the Eagle Project have not seen these slides until today. I did send them to the AMSAT board people last night because that's when I finished preparing the last of them. Very much a work in progress. I reserve the right to change my mind, especially if I've violated any fundamental laws of physics, which could easily have happened. Okay, this is a slide that came from them. They suggested a couple of areas that we should look at, namely this little chunk here and that little chunk there. And so it was sort of a, what can we do with that? Which morphed into this being my suggested configuration. In addition to those two spaces, I asked for a horn, C-band horn. Somehow the lettering didn't fit in the box in this translation. I don't know. I love PowerPoint. Bill Gates got me again. That says possible feed in LNA for C-band receive, which would make use of this spot grid dish that they have for receive. I broke the transmit functions and the receiver functions into two separate boxes. The one on your left, which is on the east side of the spacecraft, is the transmitter side. It's got a dish antenna. Don't know how big a dish that'll be yet. The one on the right-hand side has all of the receive stuff. It also has a dish antenna, perhaps slightly smaller dish, since it'll be at 5.7 gigahertz, and possibly some patch arrays for the lower frequencies. So it's receive and transmit in separate boxes. From the side, this is the actual spacecraft drawing from the north side. Our stuff's on the south side, but I didn't have a south side picture to use, so this is the with X-ray vision version. That puts east to the right now. And the dishes, you'll notice, are canted slightly off angle. There is some blockage from that large dish. And so I canted it eastward about 10 degrees. Transmitter over here, the receiver box with a dish antenna, and maybe the stack of patch antennas. And here it is as seen from the side, from the east side with the transmitter box. The antenna shows slightly elliptical because it's going to be tilted off angle. And that was about the best ellipse I could draw in Bill Gates' favorite software. Antennas. After looking at these sketches, their 2-meter size grid dish might block coverage from those locations. Therefore, the transmit dish and maybe the receive dish are tilted about 10 degrees east of nadir, east of straight down. That improves the downlink signal for the East Coast users, which is good, but it may cost coverage of New Zealand. I don't know how bad the blockage will be in that direction. We haven't got enough drawing details to do the cut and paste and game to find out. They provide a stable platform pointed at the Earth. Therefore, we can use fixed antennas. We don't have to use my fancy phased arrays, which were dynamically steered for the original Eagle. So a fairly straightforward dish antenna is possible. From GEO, this is just a couple of numbers so you remember it, regardless of frequency, the entire Earth corresponds to a directivity, not gain, directivity of 22 dBi. And that corresponds to a beam that has a full width of 18.3 degrees. So 22 dB of gain sort of matches the size of the Earth. From GO, 1 over R squared, differences make the nadir, the center of the beam, about 1.5 dB stronger than the station over at the limb. I just one to remember when you're doing link budget calculations that Boston is poorer off than Honolulu by about 1.5 dB. The suggested size for the boxes that they gave us were in the 36 to 64 centimeter range, 14 to 25 inch for the not well-educated Americans. Antennas in that size range are a bit too small for my caveat earlier, dishes should be bigger than 8 or 10 wavelengths. We'll still go ahead and try to use them even though they aren't optimized. It's going to take some careful diddling of the feed, and I don't know what it's going to look like exactly. Any receive antennas for the lower frequencies will probably be half-wave diameter patches. That's about all there's room for. Now, some radical new ideas. This is now going back to what transponders have we used in the past. The universal transponder, when implemented as an SDX, had a box. The central box looked like this, digital signal conditioning widget, which is really a computer. And the digital-oriented version of that same thing had this for a structure. In the following, I replace it for make note that's really a bunch of computers. Why don't we surround them by RF widgets and make that be what we fly? None of the rest of the stuff. RF in, computer, RF out. So we start with the 5 gigahertz receiver, 20 megahertz of bandwidth on the band. We'll use it all. Single high-speed A to D converter, sort of like Matt is using. 8 or 10 bits is probably enough. Downsample using a polyphase filter bank, making N subbands, perhaps N equals 32, which means 625 kilohertz width. Polyphase filter banks are implemented easily in FPGAs. And in here, if any of you get this from me, I've got a bunch of URLs on polyphase filter banks. And let me skip through this one. I was going to show you polyphase filter. Okay, now here's my conceptual design. 5 centimeter receiver and maybe 13 centimeter receiver with high-speed A to D converters, a big polyphase filter bank, a crossbar switch so that you can sit there and make some of those frequency channels usable in the digital FEC correction mode, and some of those be usable in the linear transponder mode. A digital remod for the digital channels that is probably CDMA with forward error correction. There's sort of an inverse of the polyphase filter bank that combines all of the signals together to a D to A converter, which goes out to the transmitter. And I note that the stuff inside those blocks is all done in FPGAs simply. So this ends up looking very much like the architecture that Matt has in the USERP 2. That's the skeleton idea. Does it ring your chime? Does it float your boat? Well, please let me know. Thank you.
Question would be, what does they get out of this?
Money.
Money? Do they get
Part of what they've found is that they don't have as much in the way of weight constrictions as they had before, and if they can turn unused space into possible revenue, they're very interested in talking to us. Part of our model that I didn't show here says that one community that might be very interested in these capabilities is the emergency communication community. And there has been some hope that if we can at least talk about a program where we can mention their name, Homeland Security might be very interested in this being the way that the amateurs can supply pretty fast, ready reaction. Considering the billions that they've spent trying to make interoperable radios and the relatively low success rate, they may just be willing to loan us something that's in the 10 to the 6th to 10 to the 7th dollar range, we hope. But we haven't talked to them yet, so this is, like I said, this is my thing, and since I know some of you had heard about that concept of you getting disaster money, I thought you might like to see what one possible configuration on the hardware might look like.
Is there any connection between our housekeeping computer and control and theirs? Or?
No, they're basically, they'll have an on-off switch, and that's about all.
Okay.
But you'll notice it was only RF and digital widgets that we have to supply. That sure does make it much more of an amateur radio project.
No rocket motor.
No rocket motors, that's right. We are not always the best rocket scientists.
Well, thank you very much, Tom. That's an exciting project. I really hope to see that come to fruition.